Hi all. In the last class we had a discussion on intermediate code generation. In this tutorial we will see three address statements in detail. So we will see different types of three address statements. First one is assignment statement in the form of x equal to y operator z, where this OP operator is a binary arithmetical or logical operation and x, y and z are operands, and operator z will be applied and the result will be stored in x. Then another type of assignment instructions in three address statements is x equal to operand y. Here there is only one operand, right? So x equal to operator y. That operator can be a unary operator like unary minus or unary plus, negation or shift operator, or it can be even conversion operator like converting a fixed point number to a floating point number. Then third one is copy statements, where we will symbol initialization statements, right? X equal to y, where the value of y will be assigned to x. Then we have unconditional jump statements, that is without any checking we will be going to a particular label. The control will be transferred to a particular label. So go to L when this statement is executed. Wherever that label is, control will be transferred to that. So this is also a type of three address statement. Now next is conditional jump. So if x relational operator y, then go to L. Okay. So when that relational operator evaluates to 1, okay, if that if condition evaluates to 1, then it will go to label L. Otherwise it will go to other statement after the if condition, right? Next is procedure call and return. So a general form of procedure is like this. We have a function name, then we will have a set of arguments. So it is represented in three address form in this form. Okay, this parameter we will represent param. So x1, x2 param, x1 param, x2 still param xn we will write. Then we will write call p comma n, where n is the total number of arguments. Okay, then we have indexed assignments. So x equal to y of I or x of y equal to y. So these are two type of indexed assignment. So what does this mean? In the array y, a particular index we have to select, then that value is assigned to x. In this we have to assign y to a particular element of array x with particular index I, that is x of 3 equal to 2, and this is x equal to y of 3. Then address and point assignments are also one type of three address statement, that is x equal to ampersand y, x equal to y, star x equal to y. These are all address and point assignments. Now next is syntax directed translation into three address code. So we have seen syntax directed translation statements. So when we implement that into three address code, what we have to do? Okay, so uh, for example, if we consider id equal to capital E, how we will represent is id dot place equal to t, where t will be a temporary variable. Okay, in writing three address formats we'll be using so many temporary variables, right? So we will write id dot place equal to t. Now there is two types. There is id dot place will represent the name that will hold the value of id. Okay, so e dot place is a name that will hold the value of e. Similarly, one more is there, that is e dot code. Okay, so e dot code will be the sequence of three address statements evaluating e. So sequence of three address statements evaluating e will be represented in e dot code, as well as a value that hold the name, or the name that hold the value will be represented by using dot place. Okay, so in the next slide we are going to see how we can represent this. Okay, a equal to b into minus c plus b plus minus c, how we can write the SDT for that. Okay, so we are going to represent it by s dot code. So this is that is giving id equal to e. So what does this mean? S dot code equal to either it can be E dot code. That is, E dot code means a three address statement. So it can be either, we can either write the direct production itself, E giving E plus E1 plus E2 as a three address code, right? So it can be either E dot code, or we can assign the value of E to ID, right? So, or generation of ID dot place equal to E dot place. Similarly, E1 plus E2. So E dot place is equal to new term. So this new term we will be seeing in the next slide. E dot code equal to either E1 dot code or E2 dot code, or we can write assignment like generation E dot place equal to E1 dot place plus E2 dot place. This simply means E1 plus E2 equal to E1 plus E2. Similarly, everything you can self-check. Similarly, there is one more thing for while statement. Okay, so we know that when executing a while statement, a condition will be there to begin the execution. Then we will have a code. Then after, if the while statement is evaluates to false, then some set of statements will be there, right? So is s dot begin, it will represent the initial or the beginning of that while. S dot after is a set of codes after the while statement, and this is a set of code within the while. So s dot begin e dot code, if e dot place is equal to 0, then go to s dot after. That is, if the if condition evaluates to 0, then we will go to set of statements after while. Otherwise, we will execute s1 dot code. Then after that, again, since it is a while condition, we have to go back. That is, go to s dot begin. Okay. The function new temp, we have seen new temp. It returns a sequence of distinct names t1, t2, etc. in response of successive calls. And generation of x equal to y plus z is used to represent simply the three address statement x equal to y plus z. Okay. Similarly, the discussion on s dot val, what we have explained. Okay. Now, implementation of three address statements. Now, three address statements can be implemented in three ways: quadruples, triples, and indirect triples. Okay. So first is quadruples. Quadruple, from the name itself, we can imagine that there will be four values, right? So it's a record structure with four fields, which are operator, argument 1, argument 2, and result. Okay. So when we take this example, x equal to y operator z, x, y, z are operands. So this y and z are arguments, argument 1 and argument 2. Op is the operator and result is x. Okay. Then this contents of this argument 1, argument 2, and result are normally pointers to symbol table entries for the names represented by these fields. So looking at that entry, we will get the value. Now, how we can convert this into a quadruple representation? Okay. So triple and indirect triple we will see in the coming slides. First, we will see how we can convert this into a quadruple representation. So this is my equation: a plus b into c, or divided by e exponent f plus b into a. So first step is to write the three address code. So how can we generate the three address code? When evaluating such kind of expression, we have to follow Bodmer's rule. So first expression will be e into f. So I am assigning a temporary variable t1. t1 equal to e exponent f. Then next will be our multiplication. So T2 equal to B into C. Then I have to perform this division. So T3 equal to T2 by T1. Okay. So far we have this done this. So next I have to perform this multiplication. So T4 equal to B into A. Then everything is to be added. So T5 equal to A plus T3, and T6 equal to T5 plus T4. So this is the table for representing in quadruple. So there are four tables: operator, argument 1, argument 2, and result. And this is a location we have to use it in the coming types. Okay, for triple and indirect triple we will use this location. That is why I have included in this also. So location simply means where this statement is stored. So what is this statement? E exponent f t1 equal to e exponent f. So if I'm looking at this table, we can identify, or we can what quickly recognize this is the expression, right? T1 equal to e1 x e exponent f, and its location is 0. Similarly, for all the equations we can write. Okay. So exceptions. When we write this three address, sorry, quadruple, or there are some exceptions. So if the statement is equal x equal to operator y, you can see that result is x, and there is only one argument. So in that case, we will leave argument 2. Okay, argument 2 will be unused. And similarly, in the case of parameter of t1, okay, so here it is represented by placing param in the operator field and t1 in the argument 1 field. Argument 2 or result field will not be used. Neither of them, argument 2 and result field, are not used in the case of param t1. Then we have unconditional and conditional gem statements. They are represented by placing the target in the result field. Okay, where the we know it will be some labels, right? So it will be kept in the result. So next type of representation is triples. Okay, so from the name we can understand triple means only three values. So in triple representation, use of temporary variables is avoided, and instead a reference to instructions are made. So the previous slide we have seen location, right? So that reference is only used. Okay, that temporary variable t1, t2, etc. are not used. So three address statements can be represented by records with three fields: operator, argument 1 and argument 2. Okay, so since there are only three fields, it is known as triples. So advantage is that we need no need to use any temporary variable, which can save memory as well as time. But there are certain disadvantages. See, when we perform code optimization, we will have to rearrange certain code lines. Okay, so the code line which came in the third will go to 5, and which was on fourth will go to second, etc. So when we use this such kind of reference to instructions, okay, when we give reference to instructions, which will cause some problem even during optimization. So that is what which is described here. Triple representation is difficult to use for optimizing compilers, because for optimization statements need to be shuffled. For example, statement 1 can come down, or statement 2 can go up. So reference we used in the representation will change. So that is one of the disadvantage of triples. This is an example how to represent triples. The same expression I have taken, and this is the same three address code. So how we can represent is, see, I have only three columns, right? Operator, argument 1 and argument 2, and we have given location also. See, this is e exponent f, this is b into c. Now I have t2 by t1, right? So what I have written, instead of t2 I have written that b into c is in location 1, so I have written 1, and e exponent f is location 0, so I have written 0. So next is b into a, I have given b to a. Then I have a plus t3. Instead of t3, I have, this is t2 by t1, which is the location 2. I have given the location 2 here. So similarly, instead of giving that particular what value, that temporary variable, I am giving the location number. Um, a ternary operation like x of I equal to y. Okay, what I am doing is I am assigning a particular value to a particular array index. Okay, it requires two entries in triple structure. This is what, see, first is operator is index of. Okay, so this index of will x, this x is the first argument, second argument is I. So when this is executed, it will become x of I. Okay, then assign the index of 0 and y. That means x of I equal to y, and the operation is assignment operation. So next is x equal to y of I. So here what I have to do, similarly y of I has to be assigned first. So equal to yi, then I have to assign the value of x. So argument 1 is x, and y of I is at location 0, and I have written 0. Okay. This is indirect triples. This is the third form of representation. So in indirect triples, this was introduced in order to overcome the problem with triples. Okay, so we will have a particular pointer. Okay, and we will give the pointer. If we give the pointer, we do not have to we will not face the problem in optimization phase. See, what we have written is same as that of in the previous, right? So e exponent f b into c is given as 1. Then division, we are giving the location number 1 and 0 similarly, but we can see it is given within symbol brackets, right? That means content of that should be taken. So when we go to this, content of 1 is at 36, right? So similarly, content of 0 is at 35, right? So even if we shuffle the instructions, that instruction number will not affect the optimization phase. Okay, so even if this 1, 2, 104 and 3 changes, it's when we finally look up, we will get this values. Okay, so that is what it is in indirect triples. It's an enhancement of a triple representation, uses an additional instruction array to lead the pointer to triples in desired order, since it uses pointers instead of position to stage reposition the expression to produce and optimize. So this is a comparison between three type of uh, three state representations. So as we have discussed, with using quadruple notation, a three-address statement containing a temporary can immediately access the location for that temporary via symbol table. But this is not possible with triples notation. With quadruple notation, statement can often move around, which makes optimization easier. Why? How is it achieved? Because quadruple notation, the symbol table interposes high degree of indirection between computation of value and its use. Okay, so just with quadruple notation, if we move a statement computing x, the statement using x requires no change. But with triples, moving a statement will affect. This makes triple difficult to use in optimizing compiler. Okay, so that problem does not occur in indirect triples also. Statement can be moved by reordering the statement list. Now, space utilization. So when it comes to space utilization, in the case of quadruples, has direct access for the location of temporaries, and it is easier for optimization. Triples also, space efficiency is there, but in the case of optimization it's not good, and in the case of indirect triples, easier for optimization as well as space efficiency. Okay, so quadruples and indirect triples require same amount of space, but triples require less space for storage. Okay, I've understood this tutorial. Thanks for watching.